Hi, we're going to talk about something called a derivative. And a derivative is spelled in this fashion, derivative. It is equal to the slope of a tangent line. And it is also called instantaneous rate, or what I call the rate at a moment. So I'm going to take a look, and I'm first going to focus on this idea of the slope of a tangent line. And I'm going to have a graph here. And let me change my color. Red. And so I'm going to have a graph that looks like this, a curve. Let me change it like this. It's a nice curve. And I'm going to go down in this fashion. Okay. And I'm going to have right here a point C. So this point right here, if this is f of x, and then this would be f of c, this point here would be c comma f of c. And I'm going to talk about this thing called a tangent line. And a tangent line just touches that curve at that point. And it has something called slope. And normally the way we figure out slope, and m is our symbol for slope, is we would take y2 minus y1 over x2 minus x1, but the problem of the slope of a tangent line is that you only have one point. So you would have f of c, right, that's my y value, minus f of c, the same y value, over the same x value, c minus c, which is netzel. I mean, we got 0 over 0. So what we do is we get another point right here. And that point is a distance away from that point. I'm going to call x comma f of x. It's some point on the curve. Oh, it could be over here, or it could be over here. And what I'm going to do is I'm going to connect those 2 points. And I don't have a tangent line. This thing right here is called a secant line. And it's called a secant line because it goes through 2 points on the curve, and it has a slope. And that slope I can figure out to be f of x minus f of c is equal to x minus c. And that is the slope of secant line. And that would be it, except what I'm going to do is I'm going to be moving this point through the limiting process closer and closer to my original point here. It's going to be moving in that direction. So it's going to end up being very, very close. And so the way that I write that is through the, again, this is the slope of the secant line. I'm going to take the limit as x approaches c, because my x values are moving in this direction. Okay, down here is x, and I'm moving it towards c. So that's what this means here, this limiting. X is approaching c, and it's going to be f of x minus f of c as x minus c. So the limiting process allows us to say, as this is moving closer and closer, I'm going to get to a limit. And that limit is going to be the slope of a tangent line. So this right here is one of my definitions of the slope of a tangent line. All right? This right here. Now I'm going to bring up two other definitions right now. Let's again draw my curve. This is f of x. Right here is c. So I have a point here. It's going to be f of c. So this is c comma f of c. Right here I'm going to have a point. And what I'm going to do here is this right here is a little bit more than c. I'm going to call this delta x. So this spot right here is going to be c plus delta x. So this point is going to be c comma f of c plus delta x. And what's going to happen is I am going to move that yellow dot in this direction. It's going to be here to begin with, and then I'm going to move it even closer. And so what's happening is this distance is being decreased, and delta x is going to be really small. In fact, delta x is approaching 0 as these get closer and closer. So now my definition, and remember I've got this secant line, and I'll put it through that point right here. It was way over here, and now it's moving closer and closer, is as delta x approaches 0 of, notice this is my yellow point, so it's going to be f of c plus delta x minus f of c over, and this should be, I screwed up here, this should be c plus delta x, I'm sorry about that, c plus delta x minus c. Now I can simplify this because c minus c is 0. So I'm going to have f of c plus delta x minus f of c all over delta x. And that is equal to my slope of a tangent line. So that's my second definition right here, and you see that quite often. So I'm going to give you a third definition. Again, I'm going to draw my graph. here's f of x. And I'm going to call this point right here, I'm going to call this x. I'm not going to use c at all. This point right here is x comma f of x. This is the most common form of the definition. And right here, this distance right here, that, this value that's more than x, I'm going to call that distance is delta x. So this is right here is going to be x plus delta x. And again, as I move the point in this direction, this delta x is going to get smaller. So it's going to be the limit as delta x approaches 0. And this point right here, I'm going to call x plus delta x, comma, f of x plus delta x. So it's very much like the c, except I don't know what c is. And this particular form has a different purpose. It gives us what is called the general form of the derivative. In other words, it gives us a formula to compute the slope of the tangent line at any point on f of x. So I'm going to write this as f of x plus delta x minus f of x over x plus delta x minus x. And again, that can be simplified as the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And this gives me the formula of the derivative. In other words, it gives me a formula for computing the slope of the tangent line at any point on f of x.